Hi everybody, here's a supplemental video to help you with bootstrapping and how to carry that out in StatKey. Now for this video, I am assuming that you have read chapter 3 and have thought about these issues a little bit. This isn't a full-on deep lecture on each part of this. I just want to highlight some of the basics and show you where to click in things in StatKey to carry this out and to do the activity for future labs and exams. So again, please read the chapter and think about these ideas a little bit, and that should make this video a lot easier. So let's go through some of these basics here, and we will make sure that you are in good shape. Whoops, get that out of there. Great. And I think there's a little watermark down here for the online thing I'm using, so hopefully that's not in the way. Let me know if there are any audio visual problems with any of this. So to set the stage, remember that our objective right now in this part of the course is to estimate things about a population, whether or not it's the proportion of something that's in a population, like the proportion of all Minnesotans that are in a certain tax bracket, or the average age of teachers in the population of a particular school. We're starting from the standpoint of wanting to answer a particular question about a population of cases, generally people. And for now, we ask, what's the proportion of something in a population, or what is the average value of something in the population? That's our objective at this point. And one of the ways we can start to do that is by taking samples and take a sample from a population and measure the proportion of the thing we're interested in, or find the average value of the thing we're interested in. But we know that I could take a sample of Minnesotans and find out, say, what their average income is, and it might be some value. But I could take another sample of Minnesotans and find their income on average, and that average might be different than the average from the first sample that I took. And so the issue is that my average that I estimate for the income for all Minnesotans, it might jump around depending on what sample I get. So ideally, what we would do, as you hopefully write about in the book, is take a lot of samples and take a lot of different samples of Minnesotans and find out what their average income is and start to get a sense for how much sampling variability there is, so that we can get a better idea as to what the actual average income is for the population of Minnesotans. Getting a sample, though, is expensive, and it can be often impractical, especially if you want to do the ideal random sampling. So the issue is, how do we estimate variability in the population? How do I estimate how much my sample mean or my sample proportion is going to jump around with repeated samples if I can't take repeated samples? Well, there was an ingenious idea that was proposed and proved within the past few decades, and it's called bootstrapping. And bootstrapping is a method that lets us estimate how much a sample proportion or a sample mean is going to jump around over repeated samples without needing to take repeated samples. All we need to do is take one sample and carry out this thing called bootstrapping. So that sets the stage a little bit. Again, that's just sort of a high-level summary of where we're coming from and what these ideas are. So we ask the question, okay, I need to do bootstrapping. We'll see what that is. Well, what is a bootstrap sample? I mean, I know what a sample is. I can take 100 Minnesotans randomly from the state and have a sample of 100 Minnesotans. That's fine. But what is a bootstrap sample? Well, a bootstrap sample, this whole procedure is mimicking going into the population and taking a bunch of samples. So bootstrapping mimics this process of taking repeated samples from the population. And from here, then, we can estimate sampling variability and estimate, as we talked about, how much the sample mean or sample proportion is going to jump around because of sampling variability. So bootstrapping mimics this. And they are generated by this process called sampling with replacement from our original one sample using a sample size that's the same as the original. And it's kind of a mouthful. So we'll see how this works. But in general, again, the idea is we're going to do this thing called sampling with replacement and then do that so that we have the exact same sample size in our original sample. So what we assume here, the logic behind why bootstrapping works for trying to mimic taking repeated samples is that if we have a sample of these 6 dots here, what we'd like to think of in theory is that this sample is, if we repeat it a bunch of times, is just a replication of our population. So I take these 6 dots and I make a bunch of copies of those 6 dots as a sample, and I put them all together, and I think of that as mimicking, hopefully closely, my actual population that I'm working from. And this assumes 2 things. One, that the original sample is a random sample, and also that we are going to be doing something called sampling with replacement. And we will get to that in just a moment here. So, okay, how do we construct a bootstrap sample? Well, for example, we could take these 6 dots and we could put them on note cards and have them represent our original sample. 1 note card with red, 2 note cards with blue, 2 note cards with yellow, 1 note card with green. The way this works, I take these 6 cards and I shuffle them up. I draw one out. I write it down, whatever that color is. So if I draw out a yellow, I write down yellow. And I put it back so that I still have my original 6 colors, the original 6 cards. The act of putting the observation back is the with replacement part. So I'm going to continue this process of taking out a card, writing down what's on it, and putting it back until I've matched the original size of the sample, which in this case is 6. So I'm going to do this 6 times. Again, take a card out, write it down, put it back in, shuffle, take a card out, write it down, put it back in. I do that 6 times, and I am done. Those 6 colors that I have written down, that I drew from my original sample of 6, that is my bootstrap sample. The important part, again, is the sampling with replacement. Bootstrapping means after you record your observation, you put it back in your original sample, and that is sampling with replacement. I repeat these things a lot because the more often you hear them, about the rule of 3s, hear it 3 times, write it 3 times, then it starts to sink in better. So that's why I repeat this so much. So that's just making a bootstrap sample. What we want to do with it then is find out what our measure of interest is. So for example, if I wanted to estimate the proportion of blue dots in my population of dots, whatever this population is, this bootstrap sample here resulted in 1, 2, 3 blue dots. So in this bootstrap sample, if I care about measuring the proportion of blue dots, in this case, it's 3 out of 6. And that 3 out of 6 in a proportion is 0.5. 0.5 I call the bootstrap statistic. The bootstrap statistic is the proportion or mean of interest from my bootstrap sample. My original sample proportion in this case is 2 out of 6 up here, or 0.33. We'll see, I'm getting this mixed up with a different example. My original proportion is 2 out of 6, or 0.33. That's my original proportion. In this case, my bootstrap statistic is 0.5, 3 out of 6. And I could do this process again and get a bootstrap sample with maybe 1 blue, or 0 blues, or all 6 blues, because again, we're sampling with replacements, so it's going to look a little bit different than the original sample. Okay. So we can do that, and that's great. But remember that our objective is to estimate what the proportion or mean of something is in the population. And we know that we've thought about standard deviation a little bit, and we also know that repeated sampling means that I might get a different sample mean each time I take a sample from a population, or I might get a different sample proportion each time I take a sample from the population. So when we want to estimate the population mean of something or the population proportion of something, our best representation is not just a single value, because we know that there's variability. The best representation is an interval. Say, I'm just pulling numbers out of the air as an example. If I want to estimate the average income for Minnesotans who are employed, however I want to specify that population, maybe it's something like $50,000. Again, I'm just making this up. Well, just saying that we estimate the population average income to be $50,000 is interesting, but there's more to it. There's more information about, well, that one sample where it's 50,000, maybe that was just a function of that sample. Maybe if I did this again, I would get 30,000, or I'd get 70,000. So in order to take the sampling variability into account, we need to quantify how much that sample mean jumps around, or how much a sample proportion jumps around. And once we quantify that, we can come up with a plausible range where my population mean or my population proportion may be. In my example about incomes, I can come up with a plausible range of where my average Minnesotan income may be. So again, the idea is, yeah, we can take one sample and estimate what the population income is with just one value. But I know that that one sample, that's just one. I'd like to have more. I'd like to know what that sampling variability is like. So we will use a bootstrap procedure to estimate that. And that bootstrap procedure will help give us an interval to say that I am confident that the average income for Minnesotans is between this value and that value, and not just a point estimate, not just one number. So that's where this was going next. So these videos, because I don't have a paid subscription to the service, are at 15-minute chops. So I'm going to end this one here, and we'll pick it up in part 2. Thank you.